Thank you. So thank you all the brave that came early this morning. I will not spare you today nonetheless. So we'll have this theorem that I announced last time and that we'll try to explain, so we constructed those quantum representations, which were representation of mapping class group, but we have not yet explained why they were finite dimensional representation. But I gave you this theorem. So we have some natural basis of those vector spaces. So how do you get the basis? You first fix a handle body with boundary your surface sigma, and you also fix a spine of the handle body, so a trivial graph, such that when you take a tubular neighborhood of the graph, you get the handle body. And then your basis is parameterized by colorings of the edges of the graph, where each edge you color by an integer between 0 and r-2. And something that I didn't say yesterday, I forgot, the integer has to be even. So it will be colored by 0, 2, or i-3. And also, for edges that meet at a vertex, you have those inequalities. So each of those colorings gives us a specific element in the vector space, where you take the handle body and you take a colored graph in it. So the colored graph gives us linear combination of links, where whenever you have an edge colored by some integer a, you have to think of this as taking a parallel cable of that strand and putting a Jones-Wetzel idempotent Fa in here. And the conditions that you have here allow you to connect the strands without any crossing at vertices. So if you want to get a basis, you need this condition, and I will explain why we can restrict to even. This is something that is specific to the fact that I took R odd at the beginning. Okay, so before I start the proof of this, I recall that I say that whenever you have W a cobordism from sigma to sigma, we get a map. So here, since I go from sigma to sigma, I get something in the endomorphism of RTR. So we say that to get the quantum representation, here we take the cobordism, which is the mapping cylinder of an element of the mapping class group. And there are some other cobordism that I would like to consider. So here I can take a cobordism with a link in it also. And I will define some operators that are associated to simple closed curves on the surface. So whenever I have gamma, a simple closed curve on sigma, I can define T gamma, which is the map associated by the Witten-Reshetikhin-Turaev functor, where I take just surface times 0, 1, and I put the curve gamma in the middle, gamma times 1. Okay, and as we will see later, those curve operators are closely related to the Dehn twist along the image of the Dehn twist along the curve, simple closed curve gamma by the quantum representation, but they are often easier to handle. So, in particular, the nice thing with them is that we have a way that we can compute them. So I can draw a curve on the boundary of this handle body, which is the surface. So maybe I go like this and like that. So this is my curve gamma. And I have some simple rules that will allow me to compute the action of this curve gamma on those kind of elements of the vector space where I put here some colored trivial graph. So they are written in here. So whenever I have the curve that goes parallel to a strand, I can merge them and get a new trivial graph with maybe more vertices. So I get this linear combination. And also when I have some other rules that allow me to simplify the graph. So whenever I have, for example, a little triangle here with one strand which came from the merging of the curve with the graph, I can erase it and up to a factor, which will turn out to be non-zero. And well, here you see that you will be able to compute this, the action of T gamma on such elements by first merging. So if you merge this strand here, you will get a linear combination where here you can have shifted this color by plus or minus 1. And you continue merging. And at some point you will have to, the only thing that you will have will be to simplify some triangles. So here we merge twice and we see that we have a little triangle here. And once we're done with this process, we'll be able to compute explicitly the action of the curve. So I'm just saying that we have those nice operators and that are explicitly computable, and will tell us also how to explicitly compute the quantum representation later. Okay, so now that I've defined this, I go back to the proof of this theorem. So there are several steps. The first step, so normally we say that the vector space RTR of sigma, the way we find it, it was spanned by elements which are pairs M, L, where the boundary of M is a free manifold and the boundary of M is sigma, and L is a link in M. But actually, we don't need to consider any free manifold with boundary sigma. We just need to consider the handle body H. So it's spanned by pairs HL, where H is our preferred handle body with boundary sigma. So the reason for this is that you will get that if boundary of M is sigma, so in the second lecture I say that whenever we have a closed free manifold, we can say that it will be a surgery on a certain link in S3. And similarly, I can say that M is a surgery on a link in the handle body H. Okay. So when we want to close this manifold M with another manifold M prime to get a closed manifold, a surgery presentation of this M union M prime will consist of, well, taking a surgery presentation for M as a surgery on the handle body, and on the other side, also, I will have a surgery presentation for the M prime as a surgery on another handle body H prime. And well, because of the way the Reshetikhin-Turaev invariant is defined, you will get that when I look at M, so let's say M with some not K, well, this will be the same as just instead taking the handle body and adding the link colored by Kirby color omega r. So because we say that to compute the invariant, in the end we will need to take the surgery representation, color all components of the surgery representation by omega r, and at the end take the colored Kaufman bracket. So here this means that, well, it's equivalent to replace this by this, whatever, no matter with what I close M to get a closed manifold. Okay, so this is the first step. Sorry? Omega r, it was the Kirby color. So which we define as a specific linear combination of the Jones-Wenzel idempotent between 0 and r minus 2. Okay, so well, the next step is to show now that so this basis B, we'll first show that this is a spanning set. Okay, so to do that, more or less what we need to show is that we only need to consider so we have our handle body here, and we say that elements spanning the vector space are links in the handle body. The handle body has some little disk so I have curves on the surface sigma that bound disk in the handle body, and such that those disks are dual to the edges of the graph. So my graph is well, maybe right blue. Okay, so here what I want to say is that to show that this B is a spanning set, it will be equivalent to just show that you don't need to consider all links to span everything. You only need is sufficient to take links in H which are crossingless with respect to the projection on the graph. And that intersect the disks. So the disk corresponding to the edge E. C of E time, where C of E satisfies those conditions. This is just so So this is what we need to show to be able to say that this thing is a spanning set. Basically, here you could consider another family of elements in here, where instead of cabling and then adding a Jones-Van-Zyl idempotent, I just cable A times when I color by A. And basically, this would also give a basis. So the two of them, it's easy to see that there is kind of a triangular change of basis between them. So you can try to show it like show this instead. Okay, and so how do you prove this step 2? Well, I won't explain everything, but basically it's based on a lemma, which says that whenever you have LC, a colored link in S3, if L has a component colored by R-1, then the market is vanishes. If so, with the same setting, if L has a component colored by some integer I, which is, let's say, less than R-2, it won't change. The colored Kaufman bracket doesn't change. Doesn't change if you replace I by R-2 minus I. And the last point is if you have instead a three-valent graph, and well, you can, so you take a three-valent graph, colored three-valent graph, it gives you some linear combination of links by the process we explained here in S3. And we can take the colored Kaufman bracket of a three-valent graph. So if gamma C has a vertex where the neighboring edges are colored by A, B, and C, and A plus B plus C is 2R-1. Then when you take the colored Kaufman bracket of this, you get 0. Okay, so you have those identities. Maybe I explain just the first one. So here you have a link, and somewhere you have a strand colored by R-1. And then, well, besides this strand, you can have something complicated. So, but basically it will be some, can think of it as a tangle. And here is the picture of your link that contains, colored link that contains a strand colored by R-1. So here you have a tangle, and you can use the Kaufman relations to simplify the crossings. And when you do, well, you may get some comeback arcs. Once you erase the crossing, you may get something like this, where you have some comeback arc somewhere. And in this case, because of the property of the Jones-Van idempotent, this will be 0. Whenever you have a comeback arc, you get 0. And there is just one possibility to erase all crossings and get something that doesn't have comeback arc for the Jones-Van idempotent, which is to get back this thing. So here I have just r-1 strands that go from the top and back at the bottom. And here a computation that we have made showed that this thing has cohort Kaufman bracket 0. Okay. So, and you have similar, similar reasoning to prove the other properties. So now, how do we get the claim from this? So let's say we have a link in here that intersects this little disk more than r-1 times. So let's say here we want, like we have a link that intersects more than r-1 times here. So I can write that this link will be equal to following. I can say that, well, I can replace this by a linear combination of the following. I add one strand called by r-1 and some other strands to get to the number of strands that is here. And plus a linear combination of links that have strictly less intersection with this little disk. So here, there were m strands, and here there's strictly less than m strands. Some linear combination of both. So now, because no matter how I close this guy, there will be a strand called by r-1. So however I close, I will get Kaufman bracket 0. And so this guy is 0 in RTR of sigma. So this process will allow me to reduce the number of intersections with each little disk dual to the spine until everything is strictly less than r-1. And kind of in the same way, if you have the intersection with 3 neighboring disks corresponding to a vertex of the free-variant graph, you will be able to express your element in terms of something that intersects less. So in the end, using this idea, you will get to show that this B is a spanning set. Okay, so now we at least know that those quantum representations are finite dimensional. And we would like still to show that what we have is a basis. So we need to show that the B's are linearly independent. So let's get to step 3. So what I will say is that, so I can take each individual vector of my presumed basis and look at the span of this vector. So a priori, it can be a 1-dimensional vector space or a 0-dimensional vector space if this is 0. But what I say is that they are in direct sum. Okay, so my the vector in my basis, they are linearly independent if they are all non-zero. So that's what I claim. And how do I prove this? The thing is that I can view those basis elements as eigenvectors of some curve operators. So, which were the operators that I was defining before I started the proof. So here we have the spine, which gives us the trivial graph. And dual to the spine, we have those curves, which give us a pair of pants decomposition of the surface. So I will write those as alpha 1, alpha 2, alpha 3. And for the vector phi c, I color this by C1, C2, C3. So what I claim is that we have that T alpha E of phi c is the same as minus a to the 2ce plus 2 minus a to the minus 2ce minus 2 times phi c. So I claim that I have this. Yes?
Since you are now using the kernel driver, so the definition gamma is not colored?
Yeah. You can extend this definition to gamma, which is colored, but I won't need it.
So it's not the action of the Dehn.
It's not the action of a Dehn. Okay, so I have this property, and here A is theta R, sorry. So our two are fruit of unity.
So because we want gamma simple for square, but it could be non-simple.
Yeah, I could take a link in the Ficken surface. Yeah, a frame link in the Ficken surface, but yeah, in that case, yeah, the framing is the framing of the surface. Okay, so I claim that I have this property, and it comes from this identity that we talked about, well, that I wrote down before, which is that when you put a belt around a Jones-Wenzel idempotent, you get the same Jones-Wenzel idempotent, but with this factor. Okay, so I get this, and it turns out that for the so those phi c are joint eigenvectors of the operators T alpha E, and the joint eigenvalue, so the collection of eigenvalues for each E in the set of edges, they are all distinct, those joint eigenvalues. So because they are all distinct, that means that those are distinct joint eigenspaces, and thus they are indirect. So. Okay, so the last step that I need is to show that all of these vectors are non-zero. It's the only thing that remains. It's a different basis if you choose a different spine. There is a way to write down the change of basis, but it's very complicated, but it's explicit, yes. Okay, so the last step, step 4, is that all the phi c's are non-zero. Okay, so first, let's look at one particular element, which is phi 0. So I color all of the edges by 0. So to color an edge by 0, well, I have to cable it 0 time and then put the 0 Jones-Wenzel idempotent, which means that just erasing the edge. So this thing will be just the naked handle body H. Well, there is the fact that S3 can always be written as a Higard splitting of any genus. So I can write S3 as H union H prime, where H and H prime are handle bodies of genus G. So if you don't know this fact, you can take it as an exercise, like how do I find a Higard splitting of genus G of S3? And this means that, well, when I look at the pairing of H and H prime, which is the Reshetikhin-Turaev invariant of S3, which was given by this constant eta r, which is zeta r squared minus zeta r minus 2 over square root of minus r. This is non-zero. So if the pairing between those two elements is non-zero, that means that H is non-zero, that is, phi 0 is non-zero. And finally, I want to argue that if one of those vectors is non-zero, then so are all the others. How do I do this? Well, I will use some specific curve operators, which are this time not dual to the spine, but kind of parallel to the edges of the spine. So here is my spine with my interface. And I introduce some curves beta 1, beta 2, and beta 3, which look like that. And I say that for them, well, applying my fusion rules that are here, get some formulas which tell me that when I apply the curve operator, so there are two types of beta curves. There is the case where the edge goes from and to the same vertex, which is here. Well, in this case, when I apply the beta curve operator, I will have a linear combination of two terms where I shift the color by 1 up or by -1 down. And in the other case, I have something like this. I shift the color by 2 up, or by 0, or by -2. And what I claim here is that this thing is non-zero here and here. Okay. So if one of my vector is non-zero, applying this curve operator, I will. So if let's say this one is non-zero, if I apply the curve operator to the one colored by C, I will get something here which is non-zero, because there is a non-zero coefficient on this guy. And so step by step, I will get that all of the elements are non-zero. And thus, since they're all non-zero, and we already know that if they are a basis, we know that they are a basis. So this concludes the proof that those elements give us a basis of the vector space RTR of sigma, on which the quantum representation are defined. Okay, are there any questions? Because we know that the vector spaces spanned by those guys are in direct sums. We don't know yet that the vectors are non-zero, but they are in direct sums. Okay. So the next thing that I want to do is to, well, now we want to start studying the properties of the quantum representation. And the first thing that one might have in mind is, since the most simple element of the mapping class group is a Dehn twist, we would like to be able to compute the action of a Dehn twist. And so is the next thing I want to talk about. So we take gamma, a simple closed curve on sigma. What we can always do is we can complete sigma, gamma into a pair of pants decomposition of the surface. And take a spine of, well, take a handle body so that the alpha I bond disk in H, bond disk in the handle body, and take a spine of that, and we will get a basis compatible with the curve gamma. Okay. So we do that, and so we are then in the following situation. We want to compute not just any Dehn twist, but to compute this one. So we can assume that the curve is here. Well, we choose basis of our vector space so that the curve is compatible with the base. So what is the action of the Dehn twist? Well, the Dehn twist will, in this case, extend to a diffeomorphism of the handle body, not just the surface. And thus, the map for T gamma will send this colored trivalent graph to the following thing. So I have the same thing here, except I twist here, so I add a curl on this edge of the graph. It's still covered by the same thing, if you want it to see free. And well, we've seen before that when we add a full twist on a Jones-Venter idempotent, what we get is minus a to the n plus 1 squared minus 1 times fn. So here this means that the action of our Dehn twist in our basis is of the following form. We have that rho RT gamma of phi c will be minus zeta r to the CE plus 1 squared minus 1 phi c. Okay, so our Dehn twist acts diagonally in this compatible basis of the vector space. And here zeta r was a 2R fruit of unity. So this guy, which I will maybe write as UR later, this one will be a primitive R fruit. Like if you have a 2R fruit of unity, the opposite is and R is odd, the opposite is a primitive R fruit. So all of the eigenvalues of my Dehn twist are R fruit of unity. And this means in particular that I have this thing. So the thing is, for any simple closed curve, I can find a pair of pants decomposition that contains it, and thus one basis of the TQFT of the vector space RTR of sigma, on which it acts diagonally with those eigenvalues. So the fact that it's diagonal, it depends on a specific choice of basis, but then the fact that you have this property will be independent of the curve. Okay, so, but yeah, it's a question, how can you compute all of the Dehn twists in the same basis? So if you want to be able to compute a general element of the mapping class group, it will be a product of all of the Humphreys generators that we saw in Andy's talk. And so we need to be able to compute all Dehn twists at once, a priori, if we want to compute any element of the mapping class group, the image of any element of the mapping class group. So here is a way how you can do this. So notice that the Dehn twist T gamma and the curve operator associated to gamma, they are diagonal in the same basis. So I say that T gamma and rho r T gamma are diagonal in the same basis. And here the eigenvalues are the minus zeta r to the 2ce plus 2 minus zeta r. So let me write. So here the eigenvalues are minus zeta r to the 2c plus 2 minus this. And for this one, I have eigenvalues which are minus this to the c plus 1 square minus 1. So some of those eigenvalues may be the same if you take, as we will talk about later, maybe if R is prime, they are all distinct, but in general, some of them may be the same, but those ones are all distinct for C going from 0 to R minus 3. So you take a polynomial P in C of X such that P of those guys are equal to those guys. Then you have that the image of the Dehn twist will be a polynomial in the curve operator T gamma. Okay, and because we are able to compute a general curve operator using those fusion rules, we are able to compute a general Dehn twist. Okay, so now what I would like to do is to prove one of the property that I had announced for the quantum representation, which is the one that it's irreducible at R with R prime. Okay, so what happens that is special when R is prime? you have that those eigenvalues they are all distinct for C in 0 to r minus 3. So those are the even integer between 0 and r minus 2. And that means that in that case, we can express the curve operator in terms of the Dehn twist. So by exactly the same reasoning, we have that T gamma is a polynomial in rho r of T gamma. Okay, so in particular, if V inside RTR of sigma is stable by the image of the mapping class group, then it's stable by all of the curve operators, because I can express the curve operators as polynomials in the Dehn twist. Okay. Well, moreover, so if we take a collection of simple closed curves that is a pair of pants decomposition of sigma, well, we have the associated basis of RTR of sigma, and we say that the joint eigenspaces of the alpha e's are all one-dimensional. Like there is only one phi c of the natural basis that has the same joint eigenvalue. We said it during the proof before. So those are joint eigenspaces of the T alpha E. And therefore, if I have something which is stable by all of the T alpha E, well, it must be a direct sum of those lines, because those are the irreducible yeah, if I have a subspace of RTR of sigma which is stable by all of those T alpha E, it must be a direct sum of joint eigenspaces. So I know that my vector space V, well, it has to be a direct sum of such elements. In particular, it has to contain at least one phi c. If it's non-zero. But then I also know that my vector space V is stable by the actions of the other curves, the beta curves that I was using before. So it's also stable by the curve operator associated with those curves. So V is also stable by the other operators, the T beta E. And this means that if we have one vector like this in the vector space, well, by the same reasoning as before, when we apply the T beta E's, we are able to find the neighboring basis element. So, and then we can find any of the basis element in this vector space V. And thus, we get that V contains all basis element phi c. And V is then the whole vector space RT of C. Okay, so I have a little bit of time, so I can try to start explaining another property. I say that I would not spare you this morning. So, and the next property is what number that I announced. It's the asymptotic fidelity. Sorry? Yeah, faithfulness. Yeah, sorry, asymptotic faithfulness. So I recall the theorem, which is that, well, let's say G is at least 2. The intersection for all R of the kernel of the row R is equal to the center of the mapping class group, which is either trivial if G is at least 3, or the identity and the hyperelliptic involution if G equals 2. Okay, so we want to prove this thing. Well, as Andy explained, a general element of the mapping class group is something that shuffles the surface in a very complicated way. And so you might wonder, how are we able to detect that some element of the mapping class group, which might be a very long and complicated composition of Dehn twist, or something that shuffles the surface in a complicated way, how do we detect that an element of the mapping class group is not the identity? That's the first thing we have to ask ourselves before trying to prove any faithfulness property for a representation of a mapping class group. So I will start with this. So it's first fact. I say that an element of the mapping class group of sigma G is central, but for G at least 3 it will mean it's trivial. If and only if for any gamma a simple closed curve, I have that f of gamma, so it should be another simple closed curve, and I want f of gamma to be isotopic to gamma. So I say that I have this thing. And to prove this fact, well, you need what Luis explained in his talk, which is to look at what happens when you conjugate f, a Dehn twist by f. Because to be central, you know, you only need to commute with all Dehn twists, since the mapping class group is generated by Dehn twist. So if T gamma is a Dehn twist, you have that F T gamma F inverse. As we explained, this is the Dehn twist along F of gamma. And also, as Liz explained, this thing is equal to T gamma if and only if F of gamma is isotopic to gamma.
Yeah, but to prove that,
Mm.
that's a lie. You need to plot your surface pieces, and you know that each piece is fixed, and each piece, the mapping class group is more or less trivial. So I mean, having a composition that the mapping class group is just that twist along the boundary, and then you take another one, which cuts, and then you get the result, and then you prove for the Dehn.
Okay, well, well,
What did you claim?
I claim, well, I think here, maybe I don't use the if and only if here. So if I have something which,
Yeah, but you
oh,
that
yeah.
the-
Yeah, I need the hard part. That's true. But anyway, so this fact is a fact, and well, there are some well, not necessarily easy to prove, but well, you can recover from what Louis stated. And well, so we can, if we have a non-trivial element in the mapping class group of surface with genus at least 3, we will know that it will send a curve to a curve which is distinct, which is not isotopic. So the second fact is now about the quantum representations. The fact is that we can explain what happens when we conjugate a curve operator by the image of some mapping class element. So we have kind of the same statement as here. We have that we get the curve operator associated to f of gamma. And here this thing is just obtained by considering, so all of those elements are associated to some cobordism from sigma to sigma. So here this is the same as looking at the composition of the cobordism CF, the mapping cylinder of F, with this guy, with CF inverse. And, well, you can convince yourself that this is the same as this guy. So then, well, since you have this identity between composition of cobordism, you get this identity between the related operators. Okay, and I will state a third fact, which I won't necessarily explain, but this is how you prove asymptotic faithfulness. Fact 3. So for any gamma, so say you have sigma and alpha E in E Pence decomposition. And you have gamma, which is not isotopic to any of the alpha E's. So it means that it has, equivalently, you can say that it has a positive geometric intersection with one of the alpha E's. what I claim is that then T gamma is not diagonal in the basis phi c associated to the pair of pens decomposition for R big enough. Okay. So this is a claim. So the original proof of Friedman, Walker, Wang did not prove this for any gamma, but just for some special curves, which are so-called graph-like elements. But it's actually true for any curve. So it's corollary of some of the results of my thesis. And with this, we can directly conclude the proof. So let's take proof of the asymptotic faithfulness. So let's take F non-central. And we can take gamma such that F of gamma is not asymptotic to gamma. And we can take alpha E, a pair of pens decomposition of sigma, starting with gamma. So there are two cases. The curve f of gamma, it's a curve distinct from gamma. So maybe it's another of the pair of pens decomposition curve. But in that case, I know that T f of gamma is not T gamma, because I know that both are diagonal in the same basis phi c, but the eigenvalues do not match. So in that f of gamma. So in that case, I get that T gamma and Tf of gamma are diagonal, but with distinct eigenvalues. So in particular, they're different. And the other case is it's not in this set of the pair of pens decomposition curves. Then Tf of gamma is not diagonal for R big enough. And so it's not equal to T gamma for R big enough. Okay. But then this also means that rho R of F is not the identity for R big enough because of the relation that I have up there. So Tf of gamma is the conjugation of T gamma by rho R of F. And if rho R of F was the identity, I would have T gamma equal Tf of gamma. So this concludes the proof of the asymptotic faithfulness. I stop here. Sorry for going over time.